This is your presenter Asloob Mudassar, and I am presenting slide number 113 of the course on laser physics. Question is, in continuation of question 111 and question 112, discuss the threshold conditions for space-dependent rate equations for a quasi-3 level laser system. So you see that here we have to discuss the space-dependent rate equations, and we have to find the threshold conditions. The answer is, in the space-dependent model, mode distribution within the resonator can be described as absolute square of u is equal to e to the power minus r square divided by square of w naught over square root of 2, as shown in equation number 1. Rather discussing the simple case of uniform pumping, we assume that the active medium is pumped longitudinally with a beam having a Gaussian transverse profile given by equation number 102.5 and which is reproduced over here. So you can see that this will give you equation number 2 equation number 2 gives you the pump rate as a function of r and z, where z is the distance along the longitudinal direction of the cylindrical rod of the cylindrical active medium rod, and r is the distance which is away from the center of the rod. So rp of r and z is equal to nr times nt times ppe over h nu p times 2 alpha over pi into omega p square, and then e to the power minus r square over square of wp over square root of 2 and then multiplied by e to the power minus alpha z, where alpha is the attenuation coefficient along the z direction, that is along the longitudinal direction. PPE is the electric power input to the pump. Nu P is the pump frequency. Nr is the radiative efficiency. Nt is the transfer efficiency. WP is the beam spot of the pump beam, and R is the distance from the radial direction of the away from the center of the cylindrical radius. The threshold inversion condition for the space independent model will be applicable to the space dependent model, but to the average value of inversion. So you see that in the space dependent cases, we have to consider the average value of the quantities which we discuss in the case of space independent cases. So you see that the average value of inversion is equal to gamma over sigma E into L, where sigma E is the stimulated emission cross section, L is the length of the active medium rod, and gamma are the total losses within the laser cavity. So gamma is in principle the logarithmic representation or the losses in terms of natural log of the cavity, where the average is computed using the expression. For this one, you can see equation number 110.2, that if you want to calculate the average of, for example, inversion, you need to use this formula, that is the average value of inversion is equal to the integral over a of the quantities n into absolute square of u times dv divided by the same integral over a, and the integrands are absolute square of u and dv, where a is the integral is performed over the active medium rod. So this a as a subscript of the integral stands for the active medium rod. For the threshold pump conditions, we assume that an equilibrium exists between the atoms excited by the pumping and the number of atoms decaying spontaneously. So you see that these are the two quantities shown in red and blue and they must be cancel out each other and they must be equal to each other so that the equilibrium conditions is established. That is the atom excited by the pumping and the number of atoms decaying spontaneously. This is applicable to each point of the active medium at threshold and below threshold. So you see that these two conditions are shown in red and blue. They hold at the threshold conditions and even at the conditions below the threshold value. Under the condition that we set dn over dt is equal to 0 and phi is equal to 0 in equation number 111.7, this gives us the pump rate to be equal to f times nt plus n as a function of r and z divided by 1 plus f times tau. So I have given equation number 107 in the appendix. So let me show you that equation there. So this is the equation number 111.7. So you see that in this equation, if we set the value of dn over dt equal to 0, and also the phi is equal to 0, we can obtain the value of Rp, that is the pump rate, to be equal to this. And we have used this relationship as equation number 5 in our today's presentation. So we have the pump rate, but you know that in the space dependent case, we have to calculate the average value of the pump rate. To compute average value of a pump rate, we insert Rp from equation number 5 into equation number 4. That is into this equation, because this equation holds, this equation can be used for the calculation of average value of any quantity. So if you want to calculate the average of a pump rate, you can replace n by the value of Rp. So you can put R over here, you can put also R inside the integral over here. So n can be replaced by R if you want to calculate the average value of the pump rate. So we insert Rp from equation number 5 into equation number 4, replacing n by Rp, that is averaging Rp over the mode intensity distribution, and then replacing the average value of n, the average value of n with its value in equation number from equation number 3 we usually obtain. So what we do is that we use a value of Rp from equation number 5 into the equation number 4, and then we use this equation, that is the value of average value of n can be used in the resulting equations, and then we can obtain the final relationship which is shown in equation number 6. The derivation of equation number 6 has also been given in the appendix. So let me show you that equation. So you see that once you obtain equation number 5 listed over here from equation number 7 by setting dn over dt is equal to 0 and by setting phi is equal to 0, you obtain equation number 5. And if you take the average value, you need to take the average value on both sides. So here on the left hand side, we have applied the average notation, and similarly in the numerator, we have used the averages of these two quantities. So this n, the average of n as a function of r and z, can simply be written as the average of n over here in this equation. So you can see that the average of n, which we have already calculated using equation number 3, is given by gamma over sigma e into L. So we can substitute this value of average value of n over here, and then the average value of this one is calculated. Now we have the average value of the pump rate, which is equal to sigma A times NT times L plus gamma divided by sigma E plus sigma A in the parentheses multiplied by L and multiplied by tau. So this is equation number 6. And equation number 6 is what we have reproduced here, what we have reproduced in the today's presentation. So this is equation number 6. So you see that this value of Rp is what we calculated using our rate equations, which was given by equation number 111.7. by setting dn over dt is equal to 0 and by setting phi is equal to 0, we obtained the value of rp, and then we calculated the average value of equation number 5, which is shown in equation number 6. Now if we compute the average value of r, that is the average value of the pump rate using rp from equation number 113.2 and using equation number 113.4, and then computing the result with the average value of rp with one of the with the one given in equation number 113.6, we obtain the threshold pump power expression as given in equation number 103.19, and which is reported in over here in equation number 113.7. So the proof of this one is also given in the appendix. So let's consult that. So you see that we have calculated this value of already we have calculated the value of R average, which is shown in equation number 6. And this value can also be calculated. The average value of this one can also be calculated. But for that one, we have to use this relationship. That is, we have to use equation number 2. The value of rp as a function of r and z, which is given in equation number 2. We have to use this value in the expression of this in the expression over here, so that we can calculate the average value there. So using equation number 2, the average value and the expression from the average value given in equation number 4, we can calculate the average value using equation number 2, which is over here. So the average value of rp using equation number 2 is eta p times p threshold divided by h nu p multiplied by 2 over pi divide and then multiplied by within the parenthesis omega naught square plus omega p square, and then multiplied by L in the denominator. So this is the equation number 18. So you see that we have now two relationship in front of us. One, a value of average RP obtained from the rate equations. The other value of RP obtained from the expression of R as a function of expression of RP as a function of R and Z, which has been defined in equation number 2. So these are the two values. We can equate these two values of average values of RP, and then we can solve the resulting expression for the value of a P threshold. And you can see that we can find the resulting value of the P threshold to be equal to this one. So P threshold will be equal to gamma times 1 plus capital B divided by eta P. And then in the parenthesis, we have H nu P over tau. And the next term is pi times omega naught square plus omega P square divided by 2 into sigma E plus sigma A. So you see that this is also shown in equation number 103.19, but you know that here we are using this as equation number 113.7. So we have found this expression, that is the threshold pump power is given by this, as given in equation number 7, and has been explained just a minute ago in the appendix. Here where B, capital B is equal to sigma A times NT times L divided by gamma, where NT is the total population in the ground level and in the lower level and in the upper laser levels. Sigma A is the absorption coefficient, L is the length of the active medium rod, and gamma is the total losses in the cavity for one pass. Above the threshold, the condition d phi over dt is equal to 0 holds, and the average gain and the average losses then becomes equal to, that is sigma E times L times the average value of steady state value of a population inversion, which we have represented as average of n with a subscript 0. This is the steady state value. So this value holds for the values at d phi over dt and for all the values above the threshold, and this is equal to gamma, and this is equal to sigma E times L times the critical population inversion. So this can be obtained from, this relation can be obtained from equation number 3. And since in equation number 3 you will notice that the steady state population inversion will be equal to the critical population inversion. That's why the two results are equal and will be equal to gamma. So these are the left hand side, and the right hand side are the gain of the system, and gamma is the loss of the system. So here the gains are equal to the loss. It means that the number of photons in the cavity is fixed. So here, so let's define x and y for this problem. X is equal to PPE over PM threshold, which is the PPM threshold is the minimum threshold value, pump value, and PPP is the electrical power to the pump. And the equation number 10 is y is equal to P out over PS, where PS is the saturation power and P out is the power output from, for example, from mirror 2 of the cavity. These x and y has been explained earlier in the previous slide, that is in slide number 112. X gives the normalized pump power and Y gives the normalized output power. To find the minimum threshold power, which is denoted by PM threshold, M stand for minimum, TH stand for threshold, P stand for power, P stand for pump power. We impose W naught is much less than WP, where W naught is the beam waste and WP is the spot size of the pump beam. So when the beam waste is much less than the spot size of the pump beam, and under that condition, which implies that B is much less than 1. So applying these two conditions to the equation number 7, which is shown over here, equation number 7. So when we apply these two conditions to the equation number 7, we find an expression for the minimum threshold pump power, which is given by gamma over eta p times, in the parenthesis we have h nu p over tau, and then we have pi omega p square divided by 2 times of sigma a plus sigma a. You know that the PM threshold pump power is in the optical form. So this is the optical power from the pump. The saturation power PS is defined as given in equation number 110.12. So PS, which is the saturation pump, has been defined in the previous in the slide number 110 and in equation number 12, which is reproduced over here. So the pump power, so this saturation power PS is equal to gamma 2 over 2 multiplied by the beam spot size at the beam waste, which is pi times omega naught over square root of 2, the whole square of this quantity, and then multiplied by IS, which is the saturation intensity. And in the next step, we have substituted IS by its value, which is h nu over sigma E plus sigma A times tau. So this is equation number 12. X and y for this problem are related through this relationship, that is x is equal to 1 plus capital B times natural log of 1 plus y divided by y, and this whole term is divided by the denominator, which contains integral from 0 to 1 t to the power delta over 1 plus yt, and this is integrated with respect to dt. Here, where we have defined delta as the square of the ratio of beam waste to the beam spot, that is square of W naught to WP. The X and Y relationship for the quasi 3-level system reduces to a 4-level laser system when the absorption arising from the lower laser level in the quasi 3-level laser system is neglected. So you see that if we neglect the absorption from the quasi 3-level system from the lower laser level back to the upper laser level, if that is neglected, then of course it will reduce, that is X will reduce to a 4-level laser system. and this requires that B should be equal to 0, or sigma A times NT times L should be much less than gamma. So under that condition, this expression, which is given in equation number 13 for the case of a quasi 3-level laser system, will reduce to the expression which we have obtained for the 4-level laser system in one of the previous slides. The slope efficiency eta s we have defined first time in equation number 110 and equation number 17. So if you consult slide number 110 and equation number 17, you will notice that the slope efficiency eta s was defined there in the following form. That is, eta s is equal to dp out over dpp is equal to ps over pm threshold multiplied by dy over dx. Now here we can substitute the value of Pm threshold and Ps, that is the saturation power and the threshold power obtained over here in equation number 11 and equation number 12 can be used over here in this expression. That is in equation number 14, and then we obtained the following result. That is eta s is equal to eta p times gamma 2 over 2 gamma multiplied by h nu over h nu p multiplied by pi omega naught square over pi wp square and then multiplied by dy over dx. So you see that if we want to calculate the dy over dx from equation number 13, the result will be difficult in its expression, or it is laborious to calculate such a result. So we are not going to calculate that result over here, but we can identify in equation number 15 the last term. The last term in the parenthesis can be identified as the transverse efficiency. So eta t is equal to pi omega naught square over pi wp square and multiplied by dy over dx. So eta s in equation number 15 is the same as that of a 4-level laser system, because in the 4-level system we found the same expression. But you know that dy over dx may be different to calculate for the 4-level system and for the 3-level system, because for a 3-level system this expression differs from a 4-level system. So we are not going to calculate the value of dy over dx and then substitute over here and then plot this whole expression. So we are just going to give some output from that plot. That is the plot of eta t versus w naught over wp whole square reveals the following features. So we are going to discuss the findings from that plot. That is, when the square of w naught to wp is much less than 1, then eta t for a 3-level laser system tends to coincide with the eta t from a 4-level laser system. The population in the upper laser level decays through stimulated emission process to ground state, nullifying the ground state absorption to the upper laser level. Here ground state absorption means that the absorption from the lower laser level back to the upper laser level, and the laser efficiency is not degraded. That's why eta t for a 3-level laser system tends to coincide with the eta t of a 4-level laser system, because the loss which is due to the lower laser level, which is not a fast decaying level in a quasi 3-level system, that is compensated by the stimulated emission process. Now you see that in the previous we have discussed that WP, that is the ratio of WP to W naught to WP, the square of that one is much less than 1. Now we are going to discuss this condition, that at square root that at the square of W naught to WP is of the order of 1. That is, W naught is the same as WP. The eta t for a 3-level system then becomes smaller than eta t for a 4-level laser system, because the excited atoms in the wings of the inversion profile now decays spontaneously to the ground state. So you see that in this condition, the spontaneous decay is also possible. That's why the eta transfer efficiency for a 3-level system is smaller than that of the 4-level system. Now the next condition, the final condition is that at square of W naught to WP is much greater than 1. Then the XY relationship for a quasi 3-level laser system reduces to that of a 4-level laser system. See equation number 110.22, and eta t for a 3-level system becomes exactly coincides with the eta t for a 4-level system, because under that condition, that is under this condition, then b times natural log of 1 plus y divided by pi y then becomes much less than 1. So under that condition, so you see that we have finally discussed these 3 conditions, that is this condition, less than 1, then equal to 1, then much greater than 1. We have discussed these 3 conditions, and we have explained these conditions also, that how these conditions occur and what happens in the cavity under these conditions. So we have answered the query raised in the question. So this is the end of slide number 113.